Hello everyone, this is SharkNet's new user seminar. Here's the outline. I will spend some time walking you through a few slides and we will discuss what SharkNet is, where to look for information, get help. We will cover some essentials of our systems, common mistakes to avoid, and question and answers at the end. Then I will switch to a short demonstration where I will show how to do simple things on our clusters. SharkNet is one of the 7 consortia covering the whole Canada. There are 3 of these in Ontario: SharkNet, SciNet, and CAC. We are all members of Compute Canada. This is the umbrella organization. And in Ontario, we are also members of Compute Ontario. SharkNet stands for Shared Hierarchical Academic Research Computing Network and is a consortium of 19 Ontario institutions, universities and colleges, which provide advanced computing resources and HPC resources and support to academic researchers. As you can see from this map, SharkNet spans a big chunk of Ontario. At this point, we providing access to around 50,000 CPU cores, more than 300 high-performance GPUs, and our systems are connected through dedicated network, at least 10 gigabit per second or better. Now I will talk about where to look for information and get help. There are 2 main online sources of information our users should know about. One is our web portal, sharknet.ca, and there is also Compute Canada site, which is docs.computecanada.ca. So let's first cover the sharknet.ca. Probably the only useful part of this portal for our users is when you go to support and training. And there you will see a few useful features. For example, you will see the calendar, which shows the events SharkNet is hosting. Webinars like the one I'm delivering right now. We run this live every Tuesday at 2 p.m. And as you can see, they're listed on our calendar. If you click on the entry, you can see the link, which allows you to attend our webinars through special software, video, and you see the description of the event. We also run so-called general interest webinars every second Wednesday at lunchtime. And as you can see, there is one entry about the most recent one. The other useful feature on our web portal is training video channel. This is the link to the channel of SharkNet on YouTube. At this point, we have hundreds of videos, webinars, short and long ones, recorded and uploaded to our channel. They cover all kinds of topics relevant to our users, HPC, advanced research computing, and so on. And as I mentioned, general interest webinars, we run them every second Wednesday, and it's been like that for many years. And there is more than 100 of these recorded and posted on our YouTube channel. We also have quick tips and features and some other recordings, including the recording you're watching right now. And finally, on SharkNet portal, you can find information about our summer schools. We run summer schools every late May, early June. These are 5 days long events. They are free to attend. Recently, we've been doing 3 parallel streams, 5 days long. So there is lots of courses and materials available to our users. And they're targeting a wide range of user base, from students, postdocs to faculty, from beginner level to intermediate level, and sometimes even advanced level. And in terms of topics, we have a wide range from traditional HPC materials like 2-day MPI course or 2-day CUDA course, and also OpenMP. But we also have courses on cloud computing, deep learning, big data, and some domain-specific courses. Also, we cover modern languages like R, Python, MATLAB, etc. So please stay tuned. SharkNet runs these schools in one of the SharkNet sites. Usually it's between McMaster, Western, and Waterloo. Last year it was in McMaster. Next year it was going to be in another site. And since a few years back, we started running these schools together with other Ontario consortia like SciNet and CIC. As you can see, it's been a number of years. We've been running 3 summer schools every year. They have similar curriculum, not identical, but similar. We have some cross-teaching. Some of our instructors teach on all 3 schools. And Central is always University of Toronto, and East it's either Ottawa or Kingston. And then going to Compute Canada documentation site, docs.computecanada.ca. This is now the primary source of information for our users. As a SharkNet user, you have Compute Canada account. You can also access other national systems, not just the ones managed by SharkNet. There are a few clusters which are national systems, so all this documentation applies to all the national systems. You'll find very large number of tutorials and articles and description of different software, description of our scheduler. I'll talk about that later. For example, it's described in much detail here, running jobs, link to some short mini webinars, talking a lot about storage. For example, in terms of installed software, we have a very large list you can access here, available software, and many hundreds of software packages are already installed. But I can already tell you now that if something is not installed here, it doesn't mean you cannot use it. You can try to install it yourself in your file space. If you can't, you can always ask us for help, and we're going to help you to install your software. So as you can see here, there are hundreds and hundreds of software packages which are already officially installed. Another important point, most of these packages are not available by default. One has to use the respective module command to load, unload different modules, and I will cover that in my live demonstration. There are 2 ways to contact us, and through email. And one is to send email to help@sharknet.ca. But these days we prefer to be contacted by you sending email to support@computecanada.ca. Only if you know the issue you are dealing with is SharkNet specific. There are some custom hardware which SharkNet hosts which are not part of Compute Canada. In those situations, you should probably use the help@sharknet.ca. In most cases, you want to use support@computecanada.ca. And this is the way to submit an issue to our ticketing system. So once you submit email to support@computecanada.ca, a ticket is created on your behalf, and then we can continue correspondence by just answering the emails. We're going to do some follow-up. Basically, when you send such a ticket, you have to list as much information as you can, so we can start helping you quickly. Now let's switch to the essentials. We'll discuss what is available, how to connect the system which we manage, Graham, but this applies pretty much to all other national systems, and how to manage disk storage, and very importantly, how to run your jobs. In terms of environment, all our clusters are using Linux operational system, and we primarily provide cluster resources, but also some cloud resources. In terms of programming support, if you're developing software, we provide all the modern compilers, C, Fortran, MATLAB, Octave, Python, R, Java. Well, some of them are not compilers, but we provide support to all these programming languages. And if you do parallel programming, then we also provide all the mainstream HPC approaches, MPI, pthreads, OpenMP. In terms of GPU programming support, these are CUDA, OpenACC, OpenCL. As I mentioned earlier, the vast majority of software packages, and there are hundreds of them installed on our systems, are not available by default. one has to use module load, unload, and similar commands to manipulate the install packages. I will show you in my live demonstration. Very critical fact, our clusters are heavily subscribed. Actually, they're oversubscribed pretty much all the time. They've been used by hundreds and hundreds of researchers across Canada. And it is wrong to expect to log into a cluster and then to be able to just run your code. So what happens, one has to submit a job, and depending on how busy cluster is, this job will run at some point in the future. This also strongly depends on how big your job is in terms of its declared runtime, how much memory it's using, and how many CPU cores or GPUs it's requesting. More about that later. So again, it's critical aspect. Normally you can't just log in and run anything, with very few exceptions. Normally you submit a job which contains all the instructions for your code to run. So this batch process should know where to find input files, where to write output files, and it should run by itself without interactions on your side. More specifically about the national system managed by SharkNet, which is called GRAM. So here are some details. It has currently slightly more than 33,000 CPU cores. We plan to expand in a short while, so we'll be adding more CPU cores. Currently we have around 1,000 nodes. These are individual computers, and typically you have 32 CPU cores per node. Most of our nodes contain 128 gigabytes of RAM, which is on average comes to 4 gigabytes of RAM per CPU core. So when you submit a job, as long as your job uses on average 4 gigabytes of RAM or less per CPU core, you should expect a relatively short wait time when you in terms of waiting in the queue. If you request more than that, large amount of memory, expect to wait quite a bit longer, because there are few nodes which has more memory than 4 gigabytes per core. We have a few nodes with large amount of memory, and at least one with huge 3 terabyte amount of memory. But as you can imagine, the wait time to use such scarce resources will be long. In terms of GPUs, we have 320 of those P100 GPUs. And in terms of networking, all these nodes are connected through high-performance InfiniBand connector of the kinds EDR and FDR. As a new user, first thing you want to know how to log into a cluster and how to copy files back and forth. The only way to access our clusters is via SSH client. If you're using Mac or Linux, all you just to do, open a text terminal and then just type this command, SSH space, your Compute Canada username @ and then cluster name. So any national system can be accessed as long as you have Compute Canada account. Graham, Cedar, Beluga, these are immediately accessible to you once you get the account. There is also Niagara, managed by SharkNet. For that you need a special extra request. You have to request access to Niagara. But the other clusters are immediately accessible to you, and this is their address, clustername.computecanada.ca. Once you execute this SSH command, it will ask you for your Compute Canada password, and once you type it in, you're connected to the cluster. If you're sick and tired of constantly typing your password in your SSH client, there is a way to avoid that by means of running SSH key agent. You have to check either sharknet.ca or computecanada.ca web portals and just search for SSH key agent tutorials. Then you find all the information you need. If you're using Windows, there is no built-in SSH client. We highly recommend free software called MobXterm, which is a sort of Swiss Army tool for SharkNet and Compute Canada users on Windows machines. It doesn't just have SSH client, It also has SFTP to copy files from your machine to cluster and backward, and things like X Window Server, which allows you to run graphical user interface GUI applications. Normally, we don't allow users to run such applications. Normally, it's a command line execution only, but there are some exceptions. For example, we have dedicated visualization nodes on the cluster where there are special instructions to access them. I don't have time to cover it here, but for those situations, you can run GUI application, and then definitely you will need this feature of mob exterm. And by the way, if you use a Mac, you would have to install special software X Quartz to be able to use a GUI application. For Unix, everything you need is already installed. In terms of copying data, if we are talking about up to maybe a few gigabytes, then it's perfectly sufficient to use command line tools such as SCP or perhaps rsync. If it's larger than that, we recommend to use online browser-based file copying Globus. To find more details about it, please go to docs.computecanada.ca and search for Globus. There is a little bit of setup. You have to spend a few minutes setting it up, but once it's set up, you can easily copy files, large amounts of files, maybe hundreds, gigabytes, terabytes, between different clusters and between clusters in your computer. You should be aware that there are a few distinct file systems on our clusters. When you log into a cluster, you find yourself inside so-called home file system. You should be aware this is a very limited file system, and also it's a low performance file system. So you're not expected to run production runs from home file systems. It is slow and it's very limited. So it only has 50 gigabytes of quote, and you can only keep up to 500,000 files. So please do not create huge amount of tiny files. You will run into this limit. And what happens if you run into this limit? You won't be able to create any new files on home file system. And if, for example, you instructed your job to use home file system, which is highly non-recommended, and you accidentally fill up your home file system, your job will actually crash because it won't be able to write it anymore. So please avoid using home file system for running jobs. This file system is fully backed up on a daily basis. It's never been purged. Nothing is deleted there automatically. It's available by default. So once you have an account, you don't have to ask for it. And it's available on both login and compute nodes. So you can do some editing on login nodes, and then you can instruct your jobs to use it. But as I just explained, it's not recommended. The more useful file systems, probably the most useful, is so-called project file system. I will show you that there is an easy, convenient symbolic link which you can use to access your project file space. By default, each research group has quite a bit of quota. It's 1 terabyte, and principal investigator, usually faculty, PI, can request increase up to 10 terabyte for the research group. But still 500,000 files per group applies here. This is much better performing file system, so your production runs are highly recommended to use this file system to read and write files. It is backed up daily basis, same as home file system. Nothing is automatically deleted. It's available from the get-go, and it's visible from login and compute node. If you're limited by that amount of disk space, then another option is to use Scratch. It is as well performing as project, but each user has up to 20 terabyte space on Scratch and 1 million files. Can even request increase up to 100 terabyte. Very important points. This is not automatically backed up, so any problem to your files, either you accidentally delete them or hard drive dies, things like that, we won't be able to help you. So please exercise caution when using Scratch file system. Use it primarily for Scratch data from running jobs. Don't use it for something very important. Also very critical, all files older than 60 days will be automatically deleted from Scratch file system. And once they're gone, they're gone. We are not gonna be able to help you to recover these files. Again, don't keep anything important in the Scratch file system. It is available by default and visible from all nodes. Finally, there is so-called nearline space. How to access it depends on the cluster. I don't have time to describe it. You should look up information on computecanada.ca documentation portal. But basically, this is the way to offload your files for archiving into our tape library. So as you can imagine, it's not instantaneous. It takes a little bit of time to both offload and download it back. So you have 5 terabyte per group quota for this tape-based storage. A very useful command, quota, can be used to see if you are approaching any of these quotas. I already described what happens if you hit the quota inside home file system. You won't be able to write files anymore. If it happens inside your project or Scratch, the running jobs can still continue running, even if you go over the quota for these 2 file system. What happens? You won't be able to submit new jobs. So until you fix the problem, until you remove all these files, extra files, and reduce the consumption to below the quota, only then you will be able to run new jobs. In terms of running programs with our scheduler, which is called Slurm, I will be showing the 4 important commands in a live demonstration. I will show you how to use sbatch to submit jobs, squeue to list jobs which are running or queued, sacct to show historical data on your jobs, including the jobs which you already finished running, and also scancel. This is the command to kill jobs, whether they're queued or running. I will be showing live demonstration after I finish my slides. And just a few slides to cover. Quite common problem faced by new users is the question, why is my job not starting? I already mentioned our clusters are busy. Hundreds of researchers use them all the time. And when you submit job, typically you have to wait. If it's a small job, sometimes you just wait minutes. If it's a large job in terms of runtime, memory, and or number of CPU cores or GPUs, you may end up waiting much longer, perhaps even days. Another critical point is that as the default user, you will only have access to roughly 15% of all the CPU cycles of our clusters. The bulk of cycles are all allocated on an annual basis. It's so-called RAC process, research allocation competition. This happens every fall, let's say roughly in October. Only faculty, PIs, can apply for the whole research group. And this is for research groups which have needs exceeding the default fraction of the resources. So if you need a lot of resources, if you find yourself waiting way too long in queue to run your jobs, then you should consider, if you're PI, or talk to your supervisor if you're a student, to apply for one of those RAC applications, which is run annually every fall. Other reasons for a job to wait too long in queue are listed here. In principle, when you submit a job, when you're asking for a specific runtime, specific number of CPU cores and memory, you have to ask for exactly what you need, not for more than what you need. Because the larger amount of resources you're asking for, the longer the queue wait time becomes. In terms of runtime, if you know, let's say your job runs 1 day, then you should ask for slightly longer than that. Once your job hits the runtime limit, it is automatically killed by the system, whether it's finished running or not. So you have to give extra leeway, a little bit of extra runtime to make sure it actually finishes before it is killed. In terms of CPU cores, if it's a parallel job, it is to your best advantage to do so-called scalability study. You basically run your program using different number of CPU cores. Usually going by a power of 2 is sufficient. So let's say you run your parallel job using 8 CPU cores, 16, 32, and so on. And then you estimate what's the throughput per CPU core. And you choose the value where a throughput is still fairly decent, because the larger number of CPU cores you use, performance start deteriorating, and at some point you're just wasting CPU cycles. So this is the negative, plus you end up waiting much longer in queue, totally unnecessarily. So pick a reasonable number of cores where the code is performing pretty well, and you're still not asking for too many, so the queue wait time is not huge. Also important in terms of memory, ask for the memory you need with slightly extra, some leeway, just in case, because if you ask for too much memory, especially if it's more than 4 GB per core, you end up waiting longer in queue. And there is a technical tip here. If you are running parallel jobs which use multiples of 32 CPU cores, let's say 32, 64, and so on, then there is a trick. By default, parallel jobs go to so-called by-core partition of our scheduler, and it is a reasonably small fraction of the cluster. To access the whole cluster, one has to add a couple of commands here. So for MPI code, you have to say -- nodes equal number of nodes you're trying to use, and then -- and task per node equal to 32. If you do that, then your job goes to so-called by node partition, which covers pretty much the whole cluster. This can substantially cut down the queue wait time. Now let's talk about common mistakes beginners do. Please do not run significant programs on login nodes, and do not run programs by logging into compute nodes. Login nodes are primarily used to edit files, to compile programs, to copy files, but they're normally not used to run programs unless they're very, very short, very quick test. For longer running codes, one has to submit a job, and I will show you how to do that in live demonstration. In terms of runtime and also memory and CPU cores, I already covered that. Please ask for a reasonable amount. Don't ask for too much, because you'll wait in queue unnecessarily long time. Do not create millions of tiny files. In fact, there is now 500,000 limit in home and project file space, so actually you won't even be able to do that. If you don't know how to handle, you have lots of tiny files, you're approaching the limit, you don't know how to handle the situation, talk to us. We will be able to help you to organize your files better. And there are some more technical points here. If you're using watch command, this would be one to note. Also, when you submit many jobs in a row, please have at least 1 second interval between submission of jobs. This is specifically applies if you submit jobs inside the loop, like bash loop on your login node, and that can go much faster than 1 per second. So you have to insert a 1 second wait time, or rather sleep time, between individual submission. Do not submit jobs which are very short, less than 10 minutes, because this is wasteful. Try to bundle up your individual jobs into bigger jobs which are at least 10 minutes. Ideally, it's at least 1 hour long to minimize the waste. And if you need to run a very large number of serial jobs, so-called serial farming, we have very good tutorials available on our YouTube channel and also on our SharkNet.ca and docs.computecanada.ca web portals. Now switch into live demonstration. This is a terminal, and I have already logged into a clustergram. These instructions would apply to any of national systems like Cedar or Beluga or Niagara. When you log in, as I mentioned before, you find yourself in a home file system. You can verify that by typing pwd command, which is print working directory, and you can see I'm inside my /home/ my username SYM file system. And you can use command disk free h dot means the current directory. This is a disk-free command. And you can see the whole file system. It's not my code, but it's what is available to all users. Is fairly small amount, only 64 terabytes, and it's currently 59% full. I mentioned before, this file system can be used to edit files, to compile programs, to submit jobs, to copy files, but normally you do not run any programs here. For that, you go to your project or Scratch file system. And there are convenient symbolic links provided inside your home file system. I'm gonna list them here using ls, list file command, -l. And one symbolic link is project, and the other one is Scratch. So you can see these are symbolic links. These are not actually subdirectories inside the home directory, but this is a link which points to a different file system. And if you go to your project link, even though it looks like you're still inside your home file system, but actually your switch file system, you're inside much larger project file system. You can verify that by executing command disk-free. As you can see, now we're in a file system which has the total size of 12 petabytes, so it's much larger than home file system. And it's currently used at 90%, so it's almost full. This is the primary file system for users to submit jobs, to run their jobs. It is high performance, and if you remember, it has 1 terabyte quota per research group, can be increased up to 10 terabyte if such a request is made. And then I can go back to home file system and go to Scratch file system. It's yet another file system, as can be demonstrated by disk-free command. Now we can see it's smaller than project, but still fairly large, 3.2 petabyte, and it's 56% full. But this is Scratch file system, files constantly generated, expired, deleted, so consumption can fluctuate quite a bit. So going back to the home file system, now I will make a quick demonstration of our scheduler, the 4 basic commands for the scheduler. So I'm going inside my Slurm subdirectory, and there are some scripts here. These are job scripts I created to demonstrate the scheduler. So let's consider the simplest. This is the serial job script. So I'll be running a very simple serial, which means it's only going to use one CPU core program. So how to run jobs like this? Let's go inside this script using a simple text editor, which I highly recommend for beginners. It's easy to use. So every job you need to submit, or you want to submit on our clusters, requires a job script like this. So one has to create a simple, small text file containing some instructions for the scheduler. So let's see what my job serial.sh job script has. All the job scripts files have to start from this line, !, exclamation mark, /bin/bash. This tells the system that this is a bash script. So for those who know what bash scripting is, you may find it useful. Basically, you can use any bash script commands, which you can use in any bash script. You can use them inside your job script. So when you submit your job, it can execute arbitrary number of commands. Bash commands execute different codes and so on. Next, at the top of this file, you have to list a few obligatory and potentially some optional as batch arguments. You list them one argument per line. It always starts from # as batch, then it goes the command itself. In this case, it's -t to look up meaning of different as batch commands. I'm going to go back. You can use manual command, man as batch, and that will give you access to huge amount of information. There are many different commands you can use. As a beginner, you'll probably be overwhelmed, but if you're a more advanced user, you know where to look for information. So going back to my job serial script, so I'm using -t, which is the runtime I'm requesting, And the format is as follows. First, it's number of days, 0, dash, number of hours, 0, 0, column, and number of minutes, 10. So I'm requesting a very short runtime, 10 minutes long job. That means it will be automatically killed after 10 minutes of running. Second obligatory argument is dash capital A, and then you list either your supervisor account, if you're a student, or if you're a supervisor, PI, you use your own account. There are a few different accounts. If you have a rack, successful rack application, you can use specific rack accounts. But for new users, you all probably have only default account, which all start with def, dash, and then you supervise a login name. Or if you are the faculty, then it's your own login name. So these are obligatory arguments. And then there are optional. For example, for serial job, it's a good idea to request certain amount of memory. Remember I mentioned our clusters have 4 GB of RAM per core on average. So as long as you ask for 4 gig or less per core, your queue wait time will not be affected. So in this case, I'm asking dash dash, my total amount of memory I'm asking for equal to 4 GB. You can use G for gigabytes, M for megabytes, and so on. You can use different units here. And then I list one or more commands I want to execute. This is serial job, so I'm executing my simple serial hello command. Here I'm using /. This is the local. What I'm telling to the script, this command is located in the same folder as this job script. Alternatively, you could provide a full path to your command here. It doesn't have to be a single command. In this case, I'm executing 2 because this serial hello is a very short command and I want to show that the job is actually running. I'm also executing another command, sleep, for 10 minutes, which means it will be running for another 10 minutes before it finished. But if you know bash script, you can use any commands you want. You can put loops here, you can put if statements, and so on. Okay, let's try to submit this job script to the scheduler. I'm using as-batch command, space, and then the name of the job script. Or you can put a full path to your job script, for example, /home, /username, /slurm, something like that. So either way, the first argument of the as-batch command is the job script. If you are bash scripting aware, if you know bash scripting, then the tip here, you can also provide arguments to your bash script, one or more arguments, which you can process internally inside your bash script. In this case, my job script doesn't have any internal command line arguments, so this is all I need to provide. Now you can see the job has been submitted, and important piece of information, you see so-called job ID. Every job you submit gets a unique number, job ID, but it's only unique per cluster. So if you have problems with your jobs and you have to contact us, send an email to support@computecanada.ca, please provide which cluster you're using and what is the job ID of the job you're having problem with. For example, it stays in queue for way too long, or it crashed, for example, or it's hanging, it's not really running for some reason. So job ID is very important information. You have to provide it to us so we can help you faster. The second command I'm going to teach you, in addition to as-batch, is sq. sq is used to show the jobs which you have submitted and which are either queued, still waiting in line, or which are already running. Once it's finished, you can no longer see it with the sq command. There is another command for that. I'll show you in a second. sq by default shows jobs belonging to all users of the cluster, using the cluster currently, which can be thousands of jobs. It's probably not what you need. Instead, you have to say -u and then your login name. In my case, it's SYM. So it will only show jobs which belong to me. As you can see here, this job, it's the same job ID, all the details I specified, runtime 10 minutes, 1 CPU core, 4 GB of RAM, and the current status is PD, which means it's pending, it's still waiting in queue. When it actually runs, the status changes to R, running, and once it's finished, you no longer will see it with the SQ command. So I'll try again, but clusters are usually busy and it probably will take too long time to run it. Instead, I'm going to kill it. So you will learn the third Slurm command, which is scancel. Scancel can be used to kill jobs which are either still queued or are already running. And you do that by providing job ID, either one or multiple. You can use scancel to kill any number of jobs. Just space separated by spaces. You list the job IDs. In this case, just one job. And there is also a dangerous version of scancel. If you say scancel -u your login name, it will kill all of the jobs on this cluster belonging to you, whether it's queued or running. So exercise extreme caution when using this command. If you're really sure you want to kill all of the jobs in the cluster, then you use this command. And finally, the fourth command I'm going to show you today is SACCT. This command is used to see the date on your historical jobs. It will also show jobs which are currently queued or running, but it's more usually used to see jobs which are older jobs, which finish running. By default, it will show only jobs belonging to you, so no need to say -u username, and only the jobs which finish running within the last 2 days. In this case, I had only one job of this kind. This is the job ID, and you can see it was cancelled by me. If you need to see information on all the jobs, then you have to check the manual for this command, and there is specifically -S option, which allows you to specify the starting moment of time since when you want to see the. So this is the command -S, and the format can be something like this: year -month -date. If you need to provide interval, you can also say -t. This is the end time. So ACCT would let you see information on all the jobs you ever run on these clusters from the beginning of time, since you just got a count here. By default, shows only for the last 2 days, but using -S and option -t, you can request information for all other older jobs. Finally, I want to show you how to handle software. I already mentioned there is a module command. To see which modules are loaded by default, one has to execute module list. And I should warn you, this CUDA module is actually not normally loaded. I added it myself. I'll show you later how you can do that for modules which you use often. But basically, all what is loaded by default, a few system level packages which you don't have to worry about. The only important things are the compiler, so which is the Intel 2016.4 version of Intel compiler. We have newer version which you can load manually. And also, if you do with MPI programming, compiling, then you need OpenMPI module. And this is fairly old version, which is the default one. What if you need to load another software which is not listed here? Let's first find out how to search for what is available. One way to do that is go back to the browser, and I showed you there is a list of software on docs.computecanada.ca website which lists all the software installed. But you don't have to do that. You can do it in situ on a cluster. For that, use module avail command. You say module avail, and then you ask for some keyword. Let's say GCC, if you want to use GCC compiler. So as you can see, there are multiple modules of GCC you can use, from the older version 4.8.5 up to bleeding edge 9.1.0. Sometimes there is a software, but a module avail doesn't show. There are some special reasons for that. There is a more powerful command. It's sort of Google search of all the software you can potentially use on the system. Use a spider command. Module spider will show you even things which module avail doesn't show, and usually you get more information. Also, you can use module spiled to get high detail information on a specific module. Let's say GCC 910. And then you can see detailed information about this particular software package. Once you found your module, the one you want to use, either from documentation website or using module avail or module spider, then you need to load it. And for that, you use command module load. There is a special rule. Because this is a compiler, our system allows only one kind of compiler officially loaded at any given time. Because you already have Intel compiler loaded, if you try to load any other compiler, either different version of Intel compiler or in this case GCC compiler, the system will let you do that, but it will automatically unload the other compilers. In this case, it unloaded the default compiler, Inter, and replaced it with GCC compiler of this specific version. So now you can see that module loaded by executing module list. And as you can see, the Intel compiler is gone. And by the way, OpenMPI is also gone because we don't have support for OpenMPI under this very recent GCC compiler. But you do see the GCC compiler loaded, so you can now use it as usual, GCC -- version, for example. And you can see this is the compiler immediately available to you. One can also add modules you frequently need. Basically, every time to log in a cluster, you want certain modules to be loaded. For that, you can add it .bash rc file, which lists all the commands which are automatically executed every time you log into the system. And as you can see here, I already put my own custom addition module load CUDA /10. So every time I log into Graham cluster, I get the default modules plus this custom module. And if you did lots of modules load and load, you may get lost. There is a quick fix to get back to the default list of modules. You execute module reset. And now you're back to the default list of modules. Finally, I'd like to demonstrate how to submit a parallel job, in this case, MPI job. I'm going back to my Slurm subdirectory, and I'm going to use another job script, job_mpi.sh. Let's have a look what's inside, how it's different from the serial job script. You see the familiar arguments, obligatory -a, your account name or your supervisor account name, -t, the runtime you request. The new options here are -n. In this case, I'm asking for 64 CPU cores. And for MPI jobs, you also have to say --mem per CPU. Remember, for serial jobs, I use --mem equal something. And this, by the way, is also used for multi-threaded job. You only use --mem. For MPI jobs, you request memory per CPU core, and in this case, I'm asking for 1 GB per CPU core. The way to execute MPI code from inside your job script is by saying srun space, and then the path to your MPI binary, either relative path as what's shown here or absolute full path. And this command will submit a 64-way MPI job to the cluster. Of course, it is a large job, 64 CPU cores, so it will definitely stay in queue for quite a while. We won't have time to see it running, but still I want to show you that it does show up in my SQ command. The runtime is 1 hour, 0 minutes, 0 second. The state is pending, it's in queue, and it's asking for 2 nodes of 64 CPU cores in total and 1 GB per CPU core. This brings us to the end of this presentation. Thanks everyone for watching.